Right now, while you are watching this, a signal is moving toward you at the speed of light. It left its source almost a full day ago. It has crossed more than 15 billion miles of empty space to get here. By the time it arrives, it is so faint that the antenna catching it has to be chilled to within a few degrees of absolute zero, just to separate it from the background static of the universe itself. The machine that sent it runs on less electricity than the bulb inside your refrigerator. That machine is 48 years old. It was built before the internet existed. It was built before most of the engineers currently keeping it alive were born. Its onboard memory holds less information than a single photograph on the phone in your pocket. Designed to last 5 years, it has lasted 48. In November of 2023, that machine sent home a signal that contained something nobody on Earth was prepared for. Not a message, not a warning, not a code. Something worse. Voyager 1 is the machine's name. In 2026, it sits close enough to the end of its life that the story of what it says last has already begun. For 5 months, the most distant object our species has ever built kept transmitting, perfectly on schedule, exactly as it always had. The carrier wave arrived, the timing was correct, the signal strength was normal. Every measurable property of that transmission said the spacecraft was alive and well, and every single bit of it was meaningless, not damaged, not partial, not garbled in the way a bad phone connection is garbled. What arrived was a repeating, locked, unbreakable pattern of ones and zeros that the same engineers who had been reading this spacecraft's mind since 1977 could not decode a single word of. Humanity's furthest voice was still speaking. It had stopped saying anything. Here's what the headlines about that period never told you. The blackout is not the part that should keep you up at night. What matters is what engineers eventually found buried inside that meaningless signal once they worked out how to ask the right question across a 46-hour delay. What matters is what all of it reveals about the actual final signal. The real one, the last one, now less than a decade away, which will not contain what almost anyone expects. Stay with me, because by the time this is over, you will understand why the most important thing Voyager 1 ever sends us is the thing that arrives after it stops talking. If deep space stories told properly are what you come here for, subscribe now and turn on notifications. We are just getting started. To understand what went wrong in 2023 and what that failure means for the signal that comes last, you have to go back to a machine that was never supposed to survive its first 5 years. September 5th, 1977. A rocket lifts off from Cape Canaveral carrying a spacecraft roughly the size of a small car, weighing about 1,700 pounds, bristling with instrument booms and a single wide dish antenna. The mission plan is modest and it is short. Fly past Jupiter, fly past Saturn, study Saturn's moon Titan, take photographs, collect measurements, and then, once the funding and the fuel and the usefulness are gone, drift into the dark and go quiet. NASA expects to be writing the mission's obituary around 1981. Nobody in that control room seriously believes they are building something that will still be filing reports in the middle of the 21st century. Voyager 1 reaches Jupiter in March 1979. What it sends back are the first genuinely close images of that planet ever captured, including active volcanoes erupting on the moon Voyager, the first volcanic activity ever observed anywhere other than Earth. 20 months later, it reaches Saturn, threads past Titan, and uses the gravity of each giant planet like a slingshot, converting the pull of those worlds into raw speed. That maneuver changes everything. The same trajectory that carried it past Titan also flung it upward, out of the flat plane of the solar system entirely, onto a path with no destination and nothing to slow it down. Cameras were switched off for good in 1990 after one final backward glance that produced the photograph now known as the pale blue dot. The planetary tour was over. Instead of shutting the spacecraft down, the way everyone had originally assumed would happen, Mission Control simply kept listening. For the next 22 years, Voyager 1 did something no object built by human hands had ever done. It kept going and going and going, outward through the thinning edge of the sun's influence, transmitting the entire time on hardware that modern engineers examine and quietly refuse to believe. Still functioning, still measuring, still sending its impossibly thin signal home across a gap that widened by nearly 1 million miles every day. Then, in 2012, it crossed a line. What Voyager 1 did that year only makes sense if you know where the solar system actually ends. Not where the planets end, where the solar system ends. Our star does not simply provide light and warmth. It constantly exhales a stream of charged particles in every direction, a supersonic wind of plasma that blows outward for billions of miles and carves an enormous bubble out of the surrounding galaxy. That bubble is called the heliosphere. Everything you have ever known sits inside it. Every planet, every moon, every asteroid, every comet, every spacecraft our civilization has ever launched, every human being who has ever lived and died. All of it exists inside a bubble of solar wind. The outer skin of that bubble, the exact place where the sun's outward pressure finally loses its argument with the inward pressure of the galaxy, is called the heliopause. That surface is the genuine physical boundary of our solar system. On August 25, 2012, at a distance of roughly 11.5 billion miles from the Sun, Voyager 1 crossed it. It became the first object in the history of our species to leave the solar system. Not as a metaphor, not as a technicality, the first physical thing we have ever built that entered the space between stars and kept transmitting after it got there. For decades, the models had described what that region would be like. These were not guesses. These were serious, rigorously tested, peer-reviewed models built by some of the best plasma physicists alive, and they broadly agreed. Interstellar space should be quiet, thin, cold, sparse, and mostly featureless. An enormous, still waiting room between star systems where almost nothing happens. Voyager 1 walked into that waiting room and found a storm. In 2017, its plasma wave instrument began registering something nobody had predicted and nobody could immediately explain. A persistent, extremely narrow band emission, a faint, continuous vibration in the interstellar plasma itself. Not a burst, not a spike that could be written off as instrument noise, not a single event. A constant signal detected year after year across a stretch of space more than 10 times the distance between the Earth and the Sun. Researchers led by Stella Koch-Ocker at Cornell University published the analysis in the journal Nature Astronomy in 2021. Their conclusion was direct. Voyager 1 was detecting the ongoing low-level oscillation of the interstellar medium itself. The team described it in plain language as a hum. Interstellar space is not silent, it rings. And it rings at a frequency that, by pure coincidence of physics, sits inside the range a human ear can process. Which means that when researchers convert those raw electric field measurements into audio, adding nothing, removing nothing, changing nothing about the underlying signal, you can literally listen to it. Sit with that for a second. Every model we have ever built to describe the universe beyond our own solar system was built from the inside looking out, from a planet, through telescopes, through mathematics, through inference. Then the very first instrument we ever physically placed on the other side of the boundary immediately told us those models had missed something fundamental, that the region between stars is not empty, not still, and not smooth, that it has structure at every scale, from meters to millions of miles, that it has texture, that it has, in a real physical sense, weather. But here is the part of this that stops being abstract and starts being personal. Those discoveries do not stay out there. They reach back here. The same bubble that separates our solar system from that turbulent environment is the bubble that protects every living thing on this planet. Consider what the heliosphere is physically doing. It deflects a significant fraction of the galactic cosmic rays streaming inward from exploded stars, the high-energy particles that shred DNA, damage electronics, and would make long-duration travel outside this bubble a far more dangerous proposition than anything we have attempted so far. Voyager 1 measured that effect directly. Inside the heliopause, galactic cosmic ray levels sat at one value. Outside, within days, they surged. The shield is real, it is measurable, and we now know precisely how much it is doing for us because we finally have a machine standing on the far side of it holding up a meter. What that machine is telling us is that the environment pressing against our shield from the outside is more turbulent, more variable, and more energetic than any model had accounted for. We do not yet know what that means for the long-term stability of the shield itself. Our sun moves through the galaxy. The material it moves through is not uniform. Over hundreds of thousands of years, this star has almost certainly passed through denser and thinner regions, and the shield has almost certainly expanded and contracted in response. Ask what that did to the biosphere, and you are no longer asking a philosophical question. You are asking a measurable one. That shift alone changes how we understand our own vulnerability as a species. All of that understanding rests on one machine, one aging, underpowered 48-year-old machine. And in November of 2023, we very nearly lost it. Now the story gets stranger. On November 14th, 2023, the team at NASA's Jet Propulsion Laboratory noticed something wrong in the daily downlink from Voyager 1. Voyager 1 was still there. The carrier signal, the raw radio tone the transmitter produces, separate from any information riding on top of it, arrived exactly as expected. Signal strength was normal. Timing was normal. By every measure of whether the machine was alive, the machine was alive. But the stream itself had collapsed into a single repeating pattern. Ones and zeros locked in a loop, carrying no science, no telemetry, no health information, nothing. Imagine calling someone you have spoken to every day for 46 years, hearing them pick up, hearing them breathing, and then hearing them produce the same meaningless syllable over and over for 5 months. That is what the Voyager team was looking at. Engineers traced the fault to the flight data system, the onboard computer responsible for gathering measurements from the instruments, packaging that information, and formatting it for transmission home. Whatever had happened, it had happened inside the part of the spacecraft that turns experience into language. This is where the physics of distance turns an engineering problem into an ordeal. In any normal repair situation, you go to the broken component and you look at it. Here, the broken component sat 15 billion miles away, unreachable by any form of transportation that exists or is likely to exist, with no possibility of a service mission in any time frame that would matter. Their only tools were radio signals, and those signals took roughly 23 hours to travel one way. 23 hours for a command to arrive, 23 hours for any response to come back, 46 hours minimum to complete a single round of communication. Think about what that engineering process actually looked like from inside that control room. You study a piece of telemetry, you form a theory about what might be wrong. You write a set of instructions designed to test that theory. You transmit those instructions. You wait 2 days. You receive whatever the spacecraft sends back. You analyze it. You discover something slightly different from what you expected. You form a new theory. You write new instructions. You transmit them. You wait 2 days again, and every single step of that process carries the knowledge that one wrong instruction, sent once across 15 billion miles of void, could permanently end the mission with no recovery possible and no second attempt available. Ever. The team worked this way for months. Through Thanksgiving. Through Christmas. Through the New Year. Through February. Nothing they tried produced anything but the same locked pattern. Then, on March 1st, 2024, they did something engineers do when they have run out of clever ideas. They sent what the team themselves informally called a poke, not a fix, not a repair command, a nudge, a signal instructing the flight data system to run through a different sequence of its own software on the chance that shaking the machine slightly might make it produce something, anything, different. 2 days later, on March 3rd, the response arrived at the Deep Space Network. At first glance, it looked like more of the same. But an engineer at the network noticed that one section of the return signal was not the repeating loop. It was different. It was still unreadable in any normal sense, and it matched no format the mission had ever used. Back at JPL, the team spent a day decoding it by hand. Here's the part almost nobody outside that building understands. What that signal contained was a readout of the flight data system's own memory. Not science, not telemetry, not a status report. Prodded into an unfamiliar routine, the spacecraft had transmitted a raw dump of the contents of its own brain, a complete picture of what was stored inside the computer that had stopped making sense. Humanity's most distant machine, unable to tell us what it was seeing, had instead sent us a photograph of its own injury. Engineers compared that memory dump against a readout from before the failure, line by line, and there it was. A single chip storing roughly 3% of the flight data system's memory had stopped working. That 3% happened to contain a portion of the software responsible for formatting and packaging science measurements for transmission. One small piece of 1970s hardware, one chip measuring a fraction of an inch, probably struck by a high-energy particle, or worn out after 46 years of continuous operation in the harshest radiation environment any human-made object has ever occupied. No alarm had gone off, no warning had been sent. It had failed quietly, without telling anyone. Nobody could repair that memory. There is no way to replace a chip across 15 billion miles. But the team realized the code could be moved. The affected software could be split into smaller sections and stored in different, still functioning regions of the spacecraft's memory. Each section would have to be individually rewritten to run correctly from its new location, then carefully reconnected so that all the pieces still functioned as a single working program, on a computer with a fraction of the memory of a modern greeting card, written in a language most working engineers have never used, through a 46-hour delay, with no undo. They began transmitting the relocated code in April 2024. On April 20th, for the first time in 5 months, Voyager 1 reported back on its own health and status in language its operators could read. By May 19th, 2 science instruments were returning real measurements again. By June 13th, all 4 remaining active instruments were back online. The spacecraft that should have died in 1981 had come back from what could easily have been its final silence, and the first thing it resumed sending was more evidence of that persistent hum in the interstellar plasma, the same unexplained emission, the same proof that the region between stars is stranger than the models say. It came back, and it went straight back to work. Here is the twist that almost nobody outside the mission team is talking about. The 2023 blackout was not the closest call. It was the first of 2. Voyager 1 does not only need power to run its instruments, it needs to stay pointed at Earth. A spacecraft that drifts even slightly off alignment stops being able to aim its dish at a planet 15 billion miles behind it, and a signal that misses Earth is a signal that does not exist. Keeping it aimed is the job of a set of small thrusters that fire tiny puffs of hydrazine dozens of times a day, correcting the spacecraft's roll and orientation. Those thrusters have been firing for 48 years. Over that time, the fuel lines feeding them have been slowly, steadily clogging with silicon dioxide, a residue shed by an aging rubber diaphragm inside the fuel tank, accumulating a little more with every firing. By 2025, mission engineers calculated that the primary roll thrusters were close to fully blocked. Attitude control could fail in the near future. If that happened, Voyager 1 would drift, the dish would wander off Earth, and the mission would end, not because the machine broke, but because it could no longer look at us. There was a backup set of roll thrusters, but they had been shut down in 2004, 21 years earlier, after a heater circuit failed and was declared unrecoverable. Nobody had powered them on since. Nobody knew whether they still worked. A deadline complicated everything, and it was not negotiable. Only NASA's Deep Space Network operates antennas powerful enough to send commands to the Voyagers, and the network's largest southern hemisphere dish, a 70-meter antenna in Canberra, Australia, was scheduled to go offline for months of upgrades. During that window, opportunities to send anything at all would be severely limited. So in March 2025, the team attempted something with a genuinely uncomfortable risk profile. They sent the command to revive thrusters that had been cold and dead for 21 years, in a system where a failed restart could have caused an unrecoverable fault, on a spacecraft with no backup to the backup. Then they waited the full round trip to find out. It worked. The dormant thrusters warmed, fired, and held. 2 near-death experiences, 2 recoveries. Both engineered blind, across a gap so large that every decision had to be made 2 days before anyone could learn whether it was the right one. Neither of them solved the actual problem, because what will eventually kill Voyager 1 is not a broken chip or a clogged fuel line. It is arithmetic, and arithmetic does not negotiate. Voyager 1 draws its power from 3 radioisotope thermoelectric generators, sealed containers of plutonium-238 that produce heat as the material decays, with that heat converted directly into electricity. At launch in 1977, they produced roughly 470 watts. Today, they produce a little over 200. They lose approximately 4 watts every year, and they will keep losing 4 watts every year, and nobody can do anything about it, because the decay rate of plutonium-238 is a property of the universe rather than a design choice. The team has known this was coming for decades. Years ago, the scientists and engineers sat down together and worked out an order, a schedule of which instruments to switch off, and when to squeeze the maximum possible scientific value out of a shrinking power supply. Of the 10 scientific instrument packages Voyager 1 carried at launch, most were shut down decades ago, once their planetary targets were behind them. In February 2025, the cosmic ray subsystem was switched off. In 2026, the low-energy charged particle instrument followed. Neither of them was broken. Both were working perfectly. They were turned off because there was no longer enough electricity to run them. These are among the hardest choices a scientific team ever has to make, because every instrument switched off is a set of questions that will never be answered, and because there is no way to turn one back on if you later decide you acted too soon. Engineers keep finding margins, sacrificing heaters, abandoning backup circuits, stripping away everything that is not load-bearing. Every year the team locates a few more watts hiding somewhere, and every year the generators take 4 back. The stated goal is to keep at least 1 instrument alive on each Voyager into the 2030s. NASA's current projection is that the generators will drop below the minimum threshold sometime early in that decade, though the agency is careful to add that the estimate could shift again, since these 2 machines have already blown past every original prediction anyone ever made about them by decades. And somewhere in those years, the last instrument will go dark, the last signal will be sent, which brings us, finally, to what that signal will actually contain. Here is the reframe, and it is the reason this story is worth half an hour of your life instead of a headline. There will be no dramatic last transmission, no farewell, no final packet of data decoded in a control room while people stand around a monitor. That is not how this ends. What happens instead is quieter and, once you understand it, considerably stranger. As power drops, the last science instrument goes dark, the spacecraft stops producing measurements, but the transmitter is not the instruments, and for some period after the science ends, Voyager 1 will most likely still be broadcasting its carrier signal, the raw radio tone underneath the data, the tone that carries no information at all, a heartbeat with no words. For a while, engineers will still detect that tone. They will know the spacecraft is there. They will know it is aimed roughly correctly. They will know nothing else because nothing else will be left to know. Gradually, that tone weakens past the point where even a 70-meter dish cooled to near absolute zero can separate it from the noise of the universe. No moment will mark it. No announcement will accompany it. There will simply be a scheduled tracking pass where the Deep Space Network points at a patch of sky, listens, and hears the background hiss of the cosmos, and nothing else. Now hold on to the number, because this is the part most people miss entirely. 23 hours. Every signal we receive from Voyager 1 is a message from its past. When the final transmission arrives on Earth, it will have left the spacecraft a full day earlier, which means that for that entire final day, we will be listening to a machine that has already fallen silent, and we will not know it. The last thing Voyager 1 ever says will reach us from a spacecraft that is already gone. What that last signal contains will not be a warning, a message, or a code. It will be a measurement of the hum, the same faint, persistent oscillation of interstellar plasma it has been recording since 2017. The sound of the space between stars, taken by the only instrument our species has ever placed there. That is the discovery nobody expected to be the ending. We sent a machine out to photograph planets, and the last thing it will ever tell us is what the emptiness sounds like. Nothing is coming behind it. No funded, approved, or launched replacement currently exists. Researchers at NASA and Johns Hopkins have spent years studying a proposed successor, sometimes called the Interstellar probe, designed from the ground up to do deliberately what Voyager did almost by accident, with instruments built specifically to map the boundary of the heliosphere. Nothing has launched. Funding and timelines remain uncertain. And even if such a mission were fully funded and launched today, it would not reach the heliopause for roughly 25 years, which means that when Voyager 1 goes quiet, the questions it raised will still be open. The only real-time window into interstellar space our civilization has ever opened will close, and it will stay closed for at least a generation. But the spacecraft does not stop when the signal does. Nothing in interstellar space slows it down. No friction, no atmosphere, no gravity strong enough to meaningfully alter its course. When the power fails, Voyager 1 keeps moving silently in a nearly straight line at roughly 38,000 miles per hour into a darkness that has no end on any human timescale. Bolted to its frame, attached to the body of that dead machine, is something that will outlast every part of this story: the Voyager Golden Record. A gold-plated copper disc, assembled in 1977 by a committee led by Carl Sagan, carrying greetings spoken in 55 human languages. 90 minutes of music drawn from cultures across the entire span of human civilization, rain falling on a forest, ocean surf, a human heartbeat, human laughter, more than 100 images physically encoded into its grooves, human anatomy, a city street, the structure of DNA. Instructions for playing it etched onto the cover, in case whatever eventually finds it has no concept of what a record is, and a map, drawn from the positions of 14 pulsars, designed to show a finder exactly where in the galaxy this planet sits. Sagan described it as a message in a bottle cast into the cosmic ocean, thrown with full knowledge that the odds of it ever being found are close to zero. It will still be traveling when the sun has swelled into a red giant and consumed the orbit of the Earth. It will still be traveling after every human city, every archive, every server, and every stone we ever carved our names into has been erased by geology and time. No other object our civilization has ever made will last as long. And this one is riding on a spacecraft that currently runs on less power than the light above your bathroom sink. So when the final radio signal fades, the one nobody will hear arrive, the one containing the hum of interstellar plasma and nothing more, the actual final message from Voyager 1 will not have been sent yet. It will still be out there, bolted to the hull, traveling, not transmitting, not broadcasting, not decaying, moving at 38,000 miles per hour, carrying the sound of human laughter through the space between stars for the next 5 billion years. We did not design it that way. We thought we were building a camera platform for a 5-year tour of 2 planets. Here's what I want you to take away from this, because there is a fact sitting in the middle of this story that is easy to miss when you are focused on the physics and the engineering. Right now, the only live scientific instrument our species has ever placed in interstellar space is 48 years old. It is powered by less electricity than the bulb above your kitchen stove. It is held together by workarounds written by people who were not born when it launched. It has been declared nearly dead twice in 3 years and has come back both times. Yet it is sending us information that is changing how we understand the universe and our own place inside it. We have built things far larger. We have built things far more powerful. We have built things that cost vastly more money and involve vastly more sophisticated technology. None of them have told us what Voyager 1 is telling us right now. Because none of them had the one thing Voyager 1 had. None of them had the audacity to keep going long enough to actually get there. There are questions about this universe that cannot be answered from a telescope on the ground, or a satellite in Earth orbit, or a probe in the asteroid belt. They can only be answered from inside, from a machine that crossed the heliopause and kept talking. We have exactly one such machine. It is old, and it is dying, and it is running on 4 watts of power. For as long as it is still transmitting, we should be listening. One machine, 4 watts, 23 hours of silence between every question and every answer. The only real question left is whether anyone is paying attention. If this is the kind of story you come here for, subscribe right now and turn on notifications because we are going deeper into the edges of what science actually knows next time. Drop a comment with the moment in this story that surprised you most. And share this with someone who still thinks the Voyagers stopped mattering in 1990 dolls, because this story deserves a great deal more than the silence it is currently getting. Thanks for watching.